So, Dan Sugalski will talk about virtual machines for high-level feature support, and something to do with Perl, I'm sure.
No, actually, there's almost nothing to do with Perl, although I will possibly listen to sympathy later on. This is the title that was in the program. I think I gave it to like 30 seconds. What the hell are you going to talk about? So it was either this or bitter cynicism. But actually, what I'm really going to talk about is handing out new toys, where we as virtual machine designers are in a position to give to the users running on us and the people writing compilers for our engines things that they might not otherwise have or might not ever want. Now we need to start with an assumptions here. These are my assumptions. First, that languages don't live in a vacuum. It's nice to say that the entire world is Java or C or Visual Basic or C#, but that's, at least as far as I'm concerned, just not true. I mean, there are people who can certainly live in that world, and that works very nicely for you if you can, but I can't, so we get this out of the way. We also like interoperability. Since we have multiple languages, it's nice to be able to talk back and forth and actually exchange data, possibly exchange control flow, all sorts of interesting things. It's very nice. And finally, features which are not shared across languages running in an environment aren't necessarily all that useful, or they're at least of limited use. It doesn't do you very much good to have, for example, to have a language that has an extraordinarily rich exception handling facility if you are calling in and out of functions written in it in a language like C, which doesn't have any exception handling facilities. You end up with all sorts of boundary issues, and that's just not so much fun. So what we'd like to do is make sure all these features are available to all the languages that are running on us. So I'll start off with some important safety tips. Nothing in this presentation I'm going to say is particularly new. The running joke when I talk to people is all the features that I'm talking about are older than I am, which isn't entirely true, but usually all the Lisp people are like, we did that 30 years ago. And I've gotten used to it. None of this is actually, none of the features that I'm going to talk about are impossible with current systems. Although having implemented many of them, it's actually very tricky in some ways. And also, none of the features that I'm going to talk about, with some rare variant exceptions, are actually implemented in any systems. That's not to say they're not necessarily implemented in any individual languages, but they are not implemented and available in a system as a whole. With the exceptions here, of exceptions to some extent, and closures also to some extent. Closures mainly because they tend to be language specific, they don't cross language boundaries, so you don't necessarily have to know they exist. And it is important to note that no, neither Lisp nor Smalltalk are considered mainstream in this particular context, because they're not. Yeah, I know, but I get less of a hiss than I usually do. I'm usually talking to folks in Cambridge and all the MIT Lisp and scheme people get out of baseball.
Smalltalk. How can you be not mainstream?
I know.
IBM sells it. It's boring and mature.
On the other hand, what else are you embedding inside of Smalltalk?
IBM sells Pascal. IBM sells API.
Anyway, before we start getting the big fight here, as far as I'm looking at, the foundations of your system drive the design of everything that lives on top of the system. Now, the foundations in this case are often provided hardware or what looks like hardware, the languages that are running on top of the system, the semantics they express, and the libraries that are available for everybody to use, or everybody to use, rather. I mean, the foundations of a system are basically the point where you say, I'm not going to go any deeper than this, or in some cases, I cannot go any deeper than this. You know, for example, if you're running on a Java virtual machine and you decide you want to change the way that Java does control flow, you can't do it. You cannot get low enough to change Java's control flow model. It's not possible in Java bytecode, and that's okay, because that's part of the point. It enforces a model. But if you don't like that model, you know, you're screwed, and that's where the foundations come in. The foundations provide you the models that are available for use. The foundations define what's easy to do, hard to do, or nearly impossible to do, either individually or shared, and it defines what you can share between languages running on top of that foundation. For example, we'll get to it later, you could, if you wanted to, on top of the JVM, implement a language that did continuations. It's possible, but it requires you to completely not use any of Java's control flow primitives and do it all yourself, which would kind of hurt. But you could do it. That would be in the nearly impossible category if you're tending to do that. But the nice thing here is our virtual machines, they play the role more or less of hardware, operating system, and system software. With the system libraries and things like that. They look to the running programs as if they were hardware CPUs, and I think if you're one of the 4 or 5 people that have an actual Java hardware machine, they really are hardware. They provide to a greater or lesser extent operating system features like device management or security. Although it's, one of the things I've been taking away from this conference is we really need to take a better look at how security is presented through virtual machine environments. Got a lot of libraries listed anyway. And the important thing is the bottom bullet point, your VMs basically have a list of things that they say these are important and they are standard. And if you want to do any of these things, you use our standards. If you want to, this is how you make a method call. If you want to make a method call, you do it this way. If you want to make a subroutine call, you do it that way. If you have an object, this is how you get an object. This is how you define classes and so on and so forth. So they provide a rich basis of functionality for compiler writers to use. They give you the things that they provide to you to things that the compiler writer otherwise can't do. For example, if you have a particular style of control flow, which is going to be harping on a lot of this, the compiler writer can't change how the control flow works. So you as a virtual machine designer get to say these are the control flow mechanisms you have. There's a list of things that compiler writers don't want to do, and we're not talking about the normal things that compiler writers don't want to do, which is basically everything. But things that they might otherwise implement if they really, really, really had to, but if they don't, that's fine. Things like you can get away with, if you're doing lexical variables, if you're doing scoped variables, you can provide support for lexical scoping either in the VM itself, or you can implement it entirely within the compiler. Either way works just fine, but if you do it in the VM, you make it easier potentially for the compiler writers. They don't have to bother. It's just more code they don't have to write. That's always good. And it also means, when you provide this rich functionality, you give a list of things that can be shared across languages without the languages necessarily having to either know about one another or in some cases neuter themselves to work within a relatively limited standard. So there you go. So none of these features are without costs, of course. Everything you implement has some price that you need to pay. Some of the prices are too high to pay. You may decide you don't want to do them. You may have a feature which is really cool but costs you 20% performance and you decide that's just not worth it. And that's just fine. You have to make a trade-off versus the features that you want, the features you need, and what they cost. The hardware certainly won't save us all the time, which is once again been a constant theme here. The hardware guys are sort of running up against physics, and physics usually wins in my experience. It is important to note, and I speak from experience here to some extent, if you're going to decide to do a feature, you should decide to go and just do it and do it right. While many of these features are expensive, doing a half-assed version of the feature is even more expensive. It will be more expensive to implement, it will be more expensive to use, and 3 years later when you decide to fix the problem because you did it wrong to begin with, you have a massive job of fixing, and oftentimes you find that you can't because you got it so wrong it's not actually possible to fix. Because say it's been welded into a standard somewhere and boy, you're stuck with it. Now, I will speak from experience here. If you're implementing a virtual execution environment, you really don't want to do all the things that I'm going to go through, and I speak from experience having done or need to do all of them. So, we'll start off with control flow is the big one. There's a lot of stuff that the execution environment, the VM, can provide or has to provide if you want real, honest-to-goodness, control flow features. Things like, not necessarily anonymous closures, but if your system does not allow you to create functions or subroutines at runtime, you can't have anonymous closures. You can't create closures at runtime. Having a proper exception system is important, especially in a cross-language environment. If you have 2 or 3 languages, you've got libraries written in one language and libraries written in another language, and your main program written in the third, if you want to have any sort of sane exception handling, all 3 languages must have a coherent and essentially identical exception model. You can get that by convention if you're really lucky. Oftentimes it just doesn't work. It's been my experience that when someone says you get it by convention, that means everybody does it a little bit differently wrong. So if you provide a mechanism in the base machine to throw and catch exceptions, you have a nice coherent exception model because only one person is implementing it, or only one system is implementing it at the VM. Things like code routines are often very difficult. if you don't have support for them in the VM, because you have basically a function or method that stops midpoint, possibly several levels of lexical scoping deep. And you just end, you return a value, but the next time you call, you have to jump right into the middle of yourself, and you start right back up again. Now, I realize you can do this to some extent without support from the VM. I mean, things like Duff's device in C, Spring, or other languages spring to mind, but it's really messy and unpleasant, and oftentimes you run into reset issues and calling problems. I found implementing coroutines, or you can cheat with threads, of course, because you can always cheat with threads, but it's a pain. It's a big pain or downright impossible to have.